So good afternoon, everyone. My name is Francesco Petruccione. I'm the interim director of NITheCS. This afternoon is a real pleasure to introduce to you as a speaker in the NITheCS Colloquium. And it's very nice to see so many people that we don't see every Monday. So please remember to come every Monday at 4, same place, same snacks, same wine. Yeah, so please, please come again next week. Yeah, there will be some other interesting talk. Dr. Anslyn John studied or did his PhD at UKZN. I don't know where he studied before that, but it's not so relevant. Also UKZN. Okay. And after which he spent some time in the US, in Michigan, more or less, or was it later? A bit later, but anyway, it was not so obvious from the bio, the chronological order. But he became then a NITHEP postdoc at some stage. Yeah, so he's been for a long time a member of the NITHECS family. And that was followed by a lecturing position in Stellenbosch, followed by a lecturing position at Rhodes. The other way around. Okay, now he's in Stellenbosch. Yeah. Sorry, it was a long day. It was a long day. And he's a cosmologist. Yeah, that I got right. Yeah. So, Anslyn, please, you are very keen to listen to your lecture. And just a reminder to the online participants, please ask your question in the Q&A. Yeah. And at the end of the talk, we will engage with them as well. Yeah. Thank you very much, Anslyn.
Okay, let's try that again. Okay, I'm Anslyn John. I'm based at the physics department at Stellenbosch University. I'm also an associate member of NITheCS, the National Institute for Theoretical and Computational Sciences. So it gives me great pleasure to be delivering the NITheCS Colloquium. As Francesco said, I was once a postdoc at the predecessor institute, which was NITHEP, back when it was theoretical physics, purely. Now it's theoretical and computational sciences. And I'm very pleased to see the organization going from strength to strength. Two of the key fields at NITheCS are theoretical physics and astronomy and astrophysics. So I'm going to have a bit to say about each of these things. Okay, so my talk is on cosmology with viscous dark matter, so I'm going to unpack that a bit. Much of it's going to be quite introductory and hopefully a bit colloquial, this being a colloquium after all. So I'm going to start off fairly smooth and gentle. It's going to get a bit bumpy and rough near the end. So fasten your seatbelts and enjoy the ride. Okay. So cosmology, that is essentially the subject of today's talk. If I were to define cosmology, I would say it was the scientific study of the origin and development of the universe on the largest scales. We have something called the standard model of cosmology. It's, when the subject reaches a certain level of maturity, we often talk about things like standard models. In cosmology, this is known as the lambda CDM. I'll tell you a bit more about what those symbols mean. But that essentially underpins a lot of modern physics and astronomy. The success of modern cosmology has been recognized by the award of 4 Nobel Prizes, and I'll briefly mention those in chronological order. Penzias and Wilson received the 1978 prize for their discovery of the cosmic microwave background radiation. Then in 2006, Mather and Smoot also shared a prize for their discovery of the black body form and anisotropy of the cosmic microwave background radiation. Back in 2011, Palmetto, Schmidt, and Rees shared the prize for the discovery of the accelerating expansion of the universe through observations of distant supernova. And finally, back in 2019, Jim Peebles' work on theoretical discoveries in physical cosmology were duly recognized. So it's a subject with a long history, and you can see there quite a few breakthroughs have been coming through and recognized at the highest level. So what do we know about the universe? Okay. This is something that really should be part of the standard physics curriculum. There's a lot of public interest in it as well. So I'm just going to describe the topic in some very, very broad brushstrokes before getting down to some specifics. Okay. Things look the same at every point in space, okay? Clearly not in this room where I see people are clustered towards the back and there are a few empty seats in the front. But if we go out on much larger scales, so larger than the Roy Plane, larger than the Western Cape, larger than the solar system, beyond the galaxy, things really do look fairly smooth and regular, okay? So there are no special or privileged positions in space. The technical term for this is homogeneity, specifically spatial homogeneity. In addition to that, things look the same in every direction I look, okay? Again, on very large scales. So there are no special directions in the universe. And the technical term for that is isotropy, okay? So there's a bit of Greek in here, spatial isotropy. And both of these observational facts are consistent with the Copernican principle, which goes all the way back to Copernicus, who proposed the heliocentric model back in the 16th century, if I recall correctly. But the Copernican principle can be summarized by this statement, that there's nothing special about our position in the universe, okay? Now that's as far as our position in space. What about our position in time? Okay, and then we can start to ask some questions. Is the universe static? Is it unchanging? Is it infinitely old? And the answer to both of these questions is a resounding no, and again, no. The universe is expanding. The expansion began 13.787 plus minus 0.020 billion years ago. This is the figure due to the collaboration involved with the Planck satellite, which is the state of the art in cosmological measurements. And for those of you who are good with numbers, this is a very precisely determined number. So there's an uncertainty here, that plus minus 0.002, and that's an uncertainty of 0.1%, roughly. So this is a very precisely determined number. And that should give you some indication of the accuracy of cosmological models. Okay, so how do we know if the universe is expanding? This is a very famous plot. This was discovered observationally by Edwin Hubble back in 1929. The Hubble Space Telescope is named after him. And here, this is a plot of velocity, speed as a function of distance. So he looked at Cepheid variables and found this very nice linear relation. This was published back in 1929. And as a result of this, you could see that the further away something is from you, the faster it's moving away from you. And that led to the famous Hubble law, which was the first observational piece of evidence that the universe was expanding. This is a very famous result. And there's some very interesting history in this as well. But was this really a surprise? Okay, it was big news, but should we really have been surprised by this? Well, if you're in the know, you know that this was, while discovered empirically by Hubble, there's this famous law with the Hubble constant, H naught. It had actually been predicted by theoretical physics sometime earlier, in fact, in the 1920s. These gentlemen, Friedman, Lemaitre, Robertson, and Walker, were experts in general relativity, a fairly new theory at that point, and they used it to develop models of the universe. And the expansion of the universe is a very natural consequence of this theory. So this was, in fact, predicted before it was discovered. This thing here, the Hubble constant, is in fact a time-dependent quantity. Well, actually the Hubble parameter is the time-dependent quantity. The Hubble constant is just the value that it happens to have today. And there's actually a bit of debate about that right now. But this all comes straight out of general relativity. So if you're doing cosmology using relativity, you would have been able to predict that the universe was expanding. This expansion law, in fact, was actually put forward by Lemaitre. There's a very interesting bit of history there. It seems that a key line in Lemaitre's paper was suppressed by the editor of that journal, who we believe was Hubble himself. And today, this has been renamed the Hubble-Lemaitre law. If you really want to know about the history of this, there's a very nice paper by Mario Livio published in Nature in 2011. So today, this is the Hubble-Lemaitre law, but H0 is still known as Hubble's constant. This is an example of one of the things I like to mention to my students, Stigler's law of eponymity, which if you've heard of, and I see some of them are here, no discovery is named after the person who discovered it. Okay, so here is perhaps the most widely used slide in all of cosmology. This is a lovely graphic by the WMAP team. This is essentially a little map of what the universe looked like in the past. Okay, so we're sitting out here today. In Big Bang cosmology, we're in a 13.77 billion year old universe, and it's been expanding, which has been represented by this little curve here. It's expanding at an accelerating rate today, which we see up here. Talk about that later. At the beginning of the expansion, we have these quantum fluctuations, which we believe turn into classical fluctuations. There's a very nice result for this in this period of accelerated expansion called inflation, which we believe happened in the very early universe. About 375,000 years after the start of the expansion, the universe became visible in the sense that radiation could be emitted and travel great distances. And the red radiation is what's known as the cosmic microwave background radiation. And then we have a period of darkness known as the dark ages. And then we have stars forming, eventually galaxies, planets, and all of us. Okay, so that's essentially a brief history of the universe. What is it made of? Okay. Well, we're all made of atoms and molecules and things we find in the periodic table. And today, if I had to look at the energy of the universe and carve up the budget, we'll see that the ordinary matter, the stuff that you and I are made of, that the world we inhabit is made of, most of the stars we see, that only makes up about 5% of the energy of the total universe. A much larger chunk, about 26%, is something called dark matter, and an even larger chunk is this thing called dark energy. So dark energy is what we term the phenomenon responsible for the acceleration of the universe, and today it makes up most of the energy of the universe. Dark matter, in a sense, makes up most of the mass of the universe. Okay, so these are very different but unknown features. Okay, so there's a lot of work to be done in figuring out what's going on in this pie diagram. Okay, all the stuff of standard periodic table behavior is sitting in here, which is of course also interesting in its own right. Lots of unsolved problems there, but we have these things we know very little about, making up most of the universe. Okay, so dark energy, that's related to the acceleration of the expansion of the universe, and the evidence for this really came about in the late in the 1990s, or as some people refer to the late 1900s. And we've got these very precise sets of measurements. There are measurements of the microwave background radiation, this radiation that was left over. Then we've got this data from supernova, and you've got these two parameters, omega matter and omega dark energy. And you've got these data sets that are very precisely determined, so the colors tell you what possible values these parameters could have according to the data. And you can see they all converge to this point here, which gives you an indication that the dark energy makes up about 70% of the total energy of the universe. And it was really impressive that we had these data sets that gave us complementary information. So one essentially will constrain the sum of these two parameters, the other will constrain the difference, and so they will intersect at right angles. And so just having one of these alone is not enough to conclude what the universe is made of, at least not to very high precision. But studies of these supernova really did bring home the idea that we live in a universe that isn't just expanding, that it's expanding at an accelerating rate. And we still don't really know why. Okay. So dark matter, which is going to be the focus of today's talk. What is that? So cold dark matter makes up most of the mass in galaxies and clusters, which are large gravitationally bound groups of galaxies. Okay. It doesn't radiate. Okay, so if a dark matter particle or a being made of dark matter was sitting in here, we would not be able to see it or interact with it, at least not by looking at it. So it doesn't radiate. So that's why it's known as dark. It's got a very small velocity dispersion, so it's not really moving at very relativistic speeds. So that's where the cold part comes in. There was an idea of warm or hot dark matter, but that is largely ruled out today. Being massive, it has a gravitational field. Okay, so our invisible dark matter friend here, while not being able to join us for the snacks afterwards, nevertheless has a mass, and so we would be able to detect that someone was there by the impression they might make on the seat, for example. Okay, so massive and invisible, but invisible to all forms of radiation. Okay, so there's a lot of it, and there's much gravity, which is essentially how we know that it's there. We see its effects through its gravitational field. And it really cannot be made out of ordinary matter, what astronomers refer to as baryonic material, which technically also includes things like electrons, even though those aren't baryons. But no known particles have the properties of dark matter. So this seems to suggest that particle physics is incomplete, and we need new members of the periodic table of particle physics, if you will. Okay, so that's what I mean by non-baryonic dark matter. If you're a physicist and you already know what baryons are, and this is a little confusing, ask an astronomer what a metal is if you want a really more confusing answer. Okay, so new particle physics seems to be required, and there are many candidates around. Theorists love inventing new ways to solve problems. And these include things like axions, various things from supersymmetry. So it's been a very active area of theoretical physics as well as astrophysics. To date, there are no direct laboratory detections. So the evidence we have for the existence of dark matter, while very strong, is all coming from indirect observations. Okay, we don't have a little particle in a box that we could poke and prod and work out its properties. It would be nice if we could. And there's some very clever attempts to try to see how dark matter could interact with ordinary matter. But to date, all the evidence is coming from astronomy. Okay, so what is this evidence? Okay, let's review it. Okay, here's a very nice little graphic. And this is the rotation curve of a galaxy called M33. And so on this axis, there's the distance from the center of the galaxy, these being large objects. It's measured in thousands of light years. And this is the velocity of parts of the galaxy. And so when people measure velocities as a function of distance, they get this curve up here. And there are various ways to do it, looking at hydrogen, looking at starlight, and so on. But if you try to work out what the mass of this galaxy is, just from adding up the mass of all the stars and all the gas, this curve should look like that. And you can see that's a huge difference. Okay, so how galaxies behave is very different from how we think they should behave based on what we think their masses are. And this actually can be explained away if most of the mass of the galaxies was in the form of dark matter. Okay, and then we can reproduce this curve very nicely. So that's one piece of evidence, and this started to accumulate in the 1970s. Looking out at much larger scales, we look at things like clusters, large groups of galaxies. We see this phenomenon known as gravitational lensing. That's the bending of light. Okay, so that's an effect purely from general relativity. If something has got a lot of mass or a lot of energy, it can warp the space-time around it. Light would usually travel in a straight line from, say, a star or a galaxy towards a telescope on Earth. But if there's a really massive object, it'll distort the space-time around it, and even the light has to respond to that. Okay, this was a prediction of general relativity as well. And so we see these really, this is a nice representation of a galaxy in the distance, a cluster with lots and lots of dark matter there, and that warps the space-time around it. So you see these distorted images, and this is a phenomenon known as gravitational lensing. And this is an example of gravitational lensing. These two things here are in fact the same object that's been lensed by something in the foreground. Here you see a bunch of arcs and so on. So there's a whole lot of lensing happening here. And this is a phenomenon that's been seen many, many times. So it's both proof of general relativity as well as the existence of dark matter. Okay, so that's another strong piece of evidence that dark matter exists. Here, this is essentially a snapshot of the universe in its infancy, if you like. It's a baby photograph. So we could take a map of the sky in the microwave, and this is what you would see. These little spots represent the temperature of the early universe. This is all in false color, of course, because right now this radiation is in the microwave. You can't see it with the naked eye. But this false color has been added on to show the slight variations in temperature, 1 part in 100,000. Okay, so some spots were hotter, some spots were colder, and so on. So if you, and this is way before stars or galaxies have formed, okay? So you just start to see the seeds of structure in this image. And you could turn this into something called a power spectrum, which is here. So this is a little technical, but what you really need to take away from this is that we can turn this map into this plot, and essentially looking at how well correlated this distribution of hot and cold spots is. How far do I have to go from this spot to that spot or how far do I have to go away to find another spot of similar temperature? So if I had a different distribution here, I'd get a different power spectrum. And the power spectrum we observe is completely consistent with there being a lot of dark matter in the universe. So if we vary the amount of matter in the universe, you would not be able to reproduce this. Okay, so that's yet another very strong piece of evidence and very precisely determined piece of data that point towards the existence of dark matter. Here's a very famous image. This is something called the bullet cluster. So these are two clusters of galaxies that are colliding. Again, this is in false color. You'd not be able to see this with the naked eye. But what you see here is bits in red or pink and bits in a bluish color. And these clusters have a lot of gas and they have a lot of dark matter. The gas collides, and so you have this thing that looks like a shock front here. And that actually only makes up part of the mass, a small fraction of the mass of these clusters. So we can infer the mass of the clusters from things like gravitational lensing. And so most of the dark matter here is actually just passing through each other. It doesn't seem to interact much with itself, whereas the gas interacts here. So this was the famous observation of the bullet cluster in the early 2000s. That's another piece of evidence for dark matter. Okay. Okay, so we know a few things about the universe. We know it's fairly smooth and very large scales, but we've also got things like clusters, galaxies, stars, and so on. So at some point, matter starts to clump together and form more dense objects. And so we know that early on it was fairly smooth, but today it looks something like this image on the right. So how did the universe go from looking like this in its infancy to this in what we might call adulthood over a period of about 14 billion years? And answering this question is one of the big questions in cosmology. And this is essentially the topic of structure formation. How did these things form out of those things? Okay. The answer actually is there's a nice intuitive explanation to this. And this actually comes from fluid mechanics. So there's no idea called the gravitational instability. So if I've got a blob of some fluid, there'll be some pressure. So the pressure between the parts of the fluid will want to push things apart. But because this fluid is made up of particles with a mass, it's going to produce its own gravitational field. So there's going to be some competition between the self-gravity of the fluid and its pressure. Okay, so this is essentially what keeps stars in equilibrium. And so this is this is a fairly old idea due to James Jeans. And it turns out that if the pressure was arranged such that it could balance the self-gravity, then you're in a nice equilibrium. But just because you're in an equilibrium doesn't mean you're in a stable equilibrium. So some of these configurations will be stable, but some will not. For those of you who've seen a bit of fluid mechanics or even Fourier analysis, there's a condition for this setup to become unstable. So if I could slightly make this slightly more dense than normal, and there'd be a little wave in it. Say I threw a stone into a pond and had these ripples. Eventually the ripples die down, but I could throw a much larger stone and cause a large wave. And in principle, I could empty out the pond. It's a similar sort of idea here. Not all configurations are stable. So if I have got little vibrations in my system, if the wavelengths are larger than some critical wavelength, which is determined by the sound speed and the density of the material, then those waves become unstable. And so this is the whole idea of gravitational instability, and this is how we think structures formed. Okay. How's my time situation? Okay. Okay, good. Okay, so we've just got to the part where the universe can start building things. Okay, so we've got another couple of billion years to go. Okay. Okay, and this turns out to be an incredibly successful idea. And if you try to predict the distribution of galaxies and clusters in our universe today, just using ordinary baryonic matter, you would not be able to produce the universe we see today. You really do need a lot of dark matter. So that's yet another piece of evidence that most of the matter in the universe is in this form of dark matter. So you need really, really large amounts of this in order to produce what we see over a period of 14 billion years. Okay. So this is an image from the famous Millennium simulation, 2005. So this involved simulating billions of particles interacting out of their own gravity and expanding. And it produced this image, which is well, one of the things it produced was this image, of course. And it really does successfully describe the distribution of matter in the universe today. Just to drive this point home, here's a very nice plot from a paper by the same people, Springle, Frank, and White, back in 2006. What you see in blue are things like the distribution of galaxies and clusters from redshift surveys. So this is all observational. This is what we see, and the bits in red are what are predicted from simulations. And if you knew nothing about the subject technically, and you would be shown these, I had to swap them around, it would be very hard to tell which was the simulation and which is the actual data. Okay, so this is an incredibly successful paradigm. Yeah. Having said that, there's still a couple of problems. Science by its very nature is incomplete, so we're always trying to push back the boundaries. Okay. So there are a couple of discrepancies between the simulations and the observations. Okay, you can't really pick it up by eye, but these authors have referred to this as the small-scale crisis. There's always a crisis or a tension or a conflict. Okay, we need very creative words to put on our proposals and capture the public imagination and so on. Okay, so what is this? What is the small-scale crisis? Well, there are a number of features, but they all seem to point to the fact that the simulations seem to predict much greater clustering on the smaller scales than we observed. And there are various bits and pieces to this. The missing satellites problems. So galaxies seem to have far fewer satellites than simulations predict. The galaxies seem to be too massive and too dense from what we see. If you look at the gravitational potentials, they appear to be much more cuspy or pointy near the center. This is the core cusp problem. And there are a bunch of others, which I'm not really going to go into any detail on. Okay, so inspired by this, some people have tried to tweak the cold dark matter paradigm. But that's not the only thing one can do. So there are a number of various solutions to the small scale crisis, as well as other problems that have showed up, these various tensions and conflicts that I've alluded to. Baryonic feedback seems to be the most successful one. That's including the effect of the baryons in the normal matter. And that really does seem to solve a lot of the problems in the small scale crisis. Some people have looked at reviving things like warm dark matter. Well, what if it's not all cold? Have a little velocity dispersion, then that might smear out the structure on the smaller scales. I'm putting these things in here just to give you a flavor of some of the things that people tried. These aren't necessarily linked to the small scale crisis, but modified Newtonian dynamics was an idea from the 1980s. It just doesn't seem to ever go away. This is the idea of changing Newton's law of gravity. Okay. People have tried this to completely remove the need for dark matter. It doesn't really work. Much more radical are things like modified gravity, where people are trying to change general relativity, and they're trying to explain not just dark matter, but dark energy. Again, it's far too early to conclude if this is going to be successful. And then a much more modest proposal is this idea that there could be some dissipative effects in the cold dark matter. So adding things like viscosity or a way for the dark matter to lose energy. And that's the sort of thing I've been working on. So what do I mean by viscosity? Okay. Well, viscosity you can simply think of as the resistance of a fluid to deformations. And some fluids are more viscous than others. Compare the way honey drips to water. Okay, one is clearly much more sticky than the other. What if dark matter had some viscosity associated with it? Okay, could this actually help us alleviate some of these problems in structure formation? Okay, so this is an idea that's been around for a bit. And in cosmology, there are generally two ways of dealing with viscosity, and there are two popular models. The first is the model due to Eckart, which was proposed all the way back in 1940. And it's much easier to use, but it has a number of problems, namely that it seems to violate relativity. So if I change something in a viscous fluid, the rest of the fluid will know about it immediately, okay? And in physics, we do not suspect that anything actually propagates faster than the speed of light, okay? So we need theories that are causal, okay? Information will take a finite amount of time to go from point A to B. So for instance, I speak into this microphone, you hear me at the back of the room, it seems instantaneous, but really the sound waves are traveling at finite speed, okay? This theory violates that. Okay. Much later, Werner Israel and John Stewart, building on earlier work by Muller, developed another theory of viscosity that was believed to have avoidance pathology. So information would travel at finite speeds. So here's where you really need to have buckled your seatbelt. So if you know a bit about fluid mechanics, you'll recognize this. So fluids moving under the influence of forces will always respect the laws of conservation of mass. Mass is neither created nor destroyed. Neither is momentum, neither is energy. And that's what these equations basically describe. If you haven't seen them before, don't panic. That's basically what it's telling us. Fluid mass, momentum, energy is conserved. That second equation is essentially Newton's second law for fluids. These fluids are going to gravitate. They're going to have mass, so they're going to create their own gravitational fields. So we describe that using something known as Poisson's equation. And then we need an equation of state to tell us something a bit more about the fluid. Typically, the pressure would depend on something like the mass density and the entropy density. And so the unknowns here are just the pressure, the mass density, the energy density, and the velocity. And this is a classic formulation of fluid mechanics. This is much broader than astrophysics or relativity. Okay, this is a very old subject with a lot of unsolved problems. But I said nothing about viscosity. So how do we incorporate viscosity or some sort of resistance to fluids? You might recall learning about things like ideal gases and realizing that they were, idealizations. Real gases do behave quite differently. This is a similar sort of thing for fluids. Okay, we have perfect fluids, but we also have imperfect fluids, and they will have things like viscosity or ways to lose energy. Okay, so we can include viscosity in the equations of fluid mechanics very easily. The mass conservation equation remains completely unchanged, but the energy and momentum equations do change. Okay, in particular, something called the stress tensor is modified. If you've never seen a tensor, don't panic. Here, I can think of this tensor as a matrix, a thing with rows and columns. And there's pressure which lives along the diagonal. So there's just P's along a diagonal and zero everything else. If I had a perfect fluid, the stress tensor would just look like that. But now that I've got viscosity, it's going to be modified by this term here, tau prime. And this viscous stress tensor will have these terms which depend on velocity gradients, as well as these numbers, these symbols zeta and mu, which represent bulk viscosity and shear viscosity. So different ways the fluid can experience resistance to motion. Okay, these parameters are usually determined empirically, or there are some theoretical models for them. Okay, so this is all classical fluid mechanics with viscosity thrown in. If I had to write those equations out explicitly, my momentum conservation equation here on the left, this is essentially mass times acceleration per unit volume. So it's the F equals ma of fluids, and that's driven by pressure, gravity, and viscous stresses. And if I had to explicitly write this out, including these viscosities, it would look like this. So you can see the equations starting to get a bit more difficult. They're quite nonlinear as well. This is what makes fluid mechanics, and particular viscosity, quite a difficult problem. If I had to look at how the energy conservation changes, there are two equivalent ways of writing it, which you may have seen. There's the energy form and the enthalpy form. If you know something about this, by all means pay attention, but just be aware that there are a number of equivalent ways of writing down our governing equations of fluid mechanics. Okay, so we're dealing with the universe, and we're also dealing with things that could be quite dense. So everything I've talked about is very classical, so there's no role for relativity in it. So how do we do fluid mechanics in relativity when things are very massive and you have things like gravitational lensing going on, or when things are moving very fast, close to the speed of light? How do we update the laws of fluid mechanics to include all these phenomena? Okay, so there's a very natural way to do this in relativity, whether you're doing special relativity, which is the theory of things moving very fast, or general relativity, which is the theory of things that are very dense or heavy. And there's some very, very nice formulations of this. Conservation of mass can be expressed by this equation. U is a fluid for velocity, so I've got a time component as well as a spatial component, so that's a very natural way to describe things in relativity as things living in four-dimensional space-times. Okay, so not just 3 dimensions of space and a clock that you carry with you, but an intricate connection between space and time. This thing here, we're going to see again. This is the stress tensor of a perfect fluid with the pressure and an energy density. And all our momentum and energy conservation laws come from this very simple equation. So it's very compact, very elegant. Again, these were for perfect fluids. So what happens if I have things like viscosity? Okay, is there a relativistic theory of dissipative fluid mechanics? And that's where the experts have begun to diverge. So Eckart devised his theory back in 1940. He had a stress tensor that looked like this. This pi represents viscous pressure. And you see it depends on the on a divergence of the velocity and this coefficient of bulk viscosity. And it was formulated based on first order deviations from thermal equilibrium. It's a fairly natural way to do things, and it's very popular. However, as I've said, it violates causality. So in that sense, it can't really be a good theory. And if I'm claiming that it's consistent with relativity. Much later, Miller and then Israel-Stewart developed another theory based on second order deviations. Again, they're using the same form of the stress tensor, where the only new thing is this bulk viscous pressure pi. But there's a much more complicated way to work out pi, and there's this transport equation here. And so this is an equation which, when I solve it, will tell me how the bulk viscous pressure changes as a function of time. Okay, so here we believed that this will actually still be a nice causal theory. And this was only proved in 2019. Okay, so a long time after the theory was developed, these authors really did establish that the Israel-Stewart theory was consistent with a causal theory of physics. Okay, so there's a lot of good reasons for considering this theory. Okay, if you're interested in, if you know something about fluid mechanics and you want to know a bit about doing it in relativity or how viscosity works, all this is described really nicely in this excellent textbook by Rizzola and Zanotti, published in 2013. For me, that is like the classic reference on relativistic hydrodynamics. Okay, so what about cosmology? Okay, I'm going to incorporate a fluid model of the universe, and I'm somehow going to add viscosity to the dark matter. How do I do that? Why would anyone want to do that? Okay, so viscosity has been considered in cosmology for quite some time. Way back in the 1970s, it was proposed as a way to solve the singularity problem, so the divide by zero at the beginning of time. That's where viscosity made its appearance. In cosmology, particle creation is also possible in strong gravitational fields. And because the bulk viscous pressure is essentially always going to reduce the total pressure of your fluid, it's a way to naturally generate an accelerated expansion. So that if you think back of that little sort of classic postcard picture of the history of the universe, we had a period of acceleration really early on, and we're going through one right now. That essentially requires an effective negative pressure. And having viscous pressure is a very natural way to do that. So bulk viscosity can very naturally give you both inflation and dark energy. Okay, so there's quite a lot of payoff for this. Why could it play a role in structure formation? Well, it's a way for a fluid to lose energy and momentum. Okay, so if the dark matter had any viscosity in it, this might start to alleviate some things like the small scale problems. It's also been proposed as a solution to the Hubble tension, which is a very contemporary, it's a very recent problem in cosmology, where two excellent groups of observers have converged on somewhat different values for Hubble's constant. So this is known as the Hubble tension. Does not seem to be going away. But people have proposed viscous dark matter as a way to solve this. And there's also an anomaly known as the edges anomaly, where again viscous dark matter has shown up. So it appears in many places. How do I do cosmology with this? Well, what I'm going to do is treat the universe as only consisting of dark matter, okay? Because I'm interested in how the structures form. So my universe will only have dark matter. I'm going to treat it as being distributed in a homogeneous and isotropic way, so there are no special places or no special directions. And I'm going to model this universe as a fluid that is expanding. So I'm going to put in Hubble's law, just like that. And so I'm going to write down what look like the equations of fluid mechanics, but I'm really applying this to the whole universe. And so mass, momentum, conservation are described here. My fluid is going to self-gravitate, so I need something like Poisson's equation. So there's a gravitational field phi created by some distribution of mass and energy. And you'll notice this is actually a Newtonian formulation. And Newtonian fluid mechanics works really well in cosmology, provided I'm only looking at things like dark matter and at fairly late times and within the causal horizon. Okay, so you can go quite far with classical fluid mechanics. If I have bulk viscosity, that needs to be some transport equation, and there are two popular theories, Eckart and Israel-Stewart, and so these transport equations are different. Okay. In the Israel-Stewart theory, the systems will have a finite relaxation time. So I throw something into a pond, the pond will start to relax, but it doesn't do so instantaneously. Okay? Things need time to settle. So in the Eckart theory, this is not the case. The system responds immediately and completely. And so any disturbances are going to travel at finite speeds in the Israel-Stewart, but infinitely fast in the Eckart theory. I'm going to model the bulk viscosity coefficient with a power law. This is a fairly standard approach. So you see it depends on the density here. And so with my collaborators, we looked at how structure formation could work with causal bulk viscosity in the Israel-Stewart theory. And I just want to highlight some of these results. There was an evolution equation for the growth of these density perturbations, which we obtained. It really did reduce to the known results when we switched off the viscosity. Doing this in the full Israel-Stewart theory gives us an evolution equation that plays the role of this. So this is some sort of equation that tells us how my structure starts to grow. And it's quite horrendous. I'll just give you a sneak peek of what the equation looks like. And there it is. Perhaps what would be more meaningful from the point of view of understanding it is this graph here. So this shows me how little overdensities evolve as a function of time. And here I've got a bunch of things happening. I've got the standard cosmological model, which is this dashed line here. And you can see as time progresses, things that are dense become even denser. The moment I make my dark matter viscous, this starts to get suppressed. If I use the Eckart theory, it gets suppressed very strongly. In the Israel-Stewart theory, for different parameter values, for different relaxation times, I get this sort of behavior, which you can see interpolates very nicely between, this idealized lambda CDM case, so just cold dark matter with no viscosity, and this extreme Eckart case with a lot of viscosity. And so you can already see this is an improvement on the Eckart model. And so you can actually, by changing these parameters, you can change the amount of clustering you have in your cosmological model. Okay. So I'm just going to wrap this up with some open questions in cosmology. Okay, one of the big questions. What is dark matter? This is made of new particles. Do we need to extend particle physics? Is dark matter made up of primordial black holes that performed very early in the universe? Okay, these are still open questions. What is dark energy? Is it due to the cosmological constant? Is it due to some sort of scalar field? Are dark matter and dark energy really just two sides of the same coin? Is there a way to unify the dark sector? Is general relativity still an accurate model of the universe? What is the ultimate fate of the universe? Are the laws of physics finely tuned? What is the nature of the Big Bang singularity? Okay, so these are the questions cosmologists deal with. What is the best physical theory of the universe? Okay, so these are some of the questions that are tackled in my research group. And since I spoke a lot about fluids being perfect or imperfect, I'd like to leave you with this this little nugget. Here's a picture of the campus. We're somewhere in this direction, I believe. That's Stellenbosch University. And for those of you who perhaps have never been here listening online, Stellenbosch is the heart of the wine country of South Africa. And our winemakers have supreme confidence in their abilities, to the extent that they occasionally produce bottles of wine with labels like this. If you go back, I think it's around equation 12 or 13, that is the stress tensor of a perfect fluid. So this is purportedly a very good bottle of wine. And with that, I will conclude. Thank you.
Thank you very much, Anslyn, for the very informative talk. I'm sure there are questions for Anslyn. And maybe we can start with questions in the audience, and then we move on to questions online. Any first volunteer to ask a question? Here we go.
Looking at the questions that you posed at the end, it seems as if a possible answer to what is dark matter can range anywhere from actually finding particles for it and so on, to completely revising how we think of physics. Are there people that work on this complete revision, not to build on, like, entirely rewrite the whole thing? Is there some work done in this direction? I don't know though how one would go about working on it, but
so the short answer to that question is yes, there are people who work on modifying or adjusting the laws of physics. The question is, how radically does one modify it? Because if one accepts the principle of verisimilitude, okay, we're going to gradually improve our theories. They work really well until they don't, and then we start to fix things at the boundaries, and so on. So that's a common technique in all of science. So people are indeed exploring, new models of physics. Like finding new particles is really doing that as well. Changing the laws of gravity is also changing the laws of physics, but it's in a sense it's a bit more radical than saying, okay, well, we've got these particles, we believe they should exist because of supersymmetry, etc. Haven't found them yet, but when they show up, they're going to solve everything. So there's a lot of work in this. It's a theorist's playground as well. What's nice is that we have strong observational and experimental work coming in as well. So we're not completely constrained.
So the winemaker should change that equation to be a curved space-time. This is the stress for Minkowski stress-time. So he would change the eta into G mu. Okay. So I think one question is, one little thing is you show the delta as function of scale factor A, but delta is a scale is a gauge-dependent quantity. So it's different in Newtonian gauge and synchronous gauge. I wonder which one that delta you mean to plot, and what is the scale that corresponds to?
Oh, the scale actually has been fixed. So we plot this for a number of different scales in our paper. So I just chose that as a representative plot. So that was for a fixed scale. But the question of gauge is that shows up in relativistic perturbation theory. This was a completely Newtonian result. So there's no gauge ambiguity there.
So it's conformal Newtonian gauge that you use.
It's not relativistic. It's Newtonian physics. Yeah.
Any other questions? Here. Sorry, I need to do my 10,000 steps.
Thanks, Anslyn. In terms of observations, do we have any idea about the distribution of dark matter, in the sense that, sure, if you look at a large galaxy, you can say there's dark matter, but do we know, does it occur, in between the, let's call it, solar systems in that galaxy? On what length scale do we know the distribution? Is there any measurements for that?
Yeah, so we actually do have fairly good inferences of the distribution. So the most popular idea is the idea of galaxies being having a halo of dark matter. So what we see electromagnetically is just a small slice of it, and there's a much more even distribution of dark matter around. And you could also see this, I didn't show this, but actually the very first piece of evidence for dark matter was the motion of galaxies within clusters. And you can plot these rotation curves. This was done by Zwicky in the 1930s, I think. And yet again, it seems that even if you look at large groups of galaxies, they're actually living in larger clumps of dark matter. Yeah, it's certainly not lying in our backyard to the extent that we could pick it up and put it in a test tube. Yeah, so we definitely have some limits on that.
Hi, Anslyn. Thanks for the talk. If I have to push you in terms of if you introduce viscosity into it, like it's a more particle-like characteristic, would there be any indications of the type of particle that can you extract information about it in terms of the particle itself that it could be in terms of the characteristics?
Yeah, that's a good question, and that's kind of part of the motivation of this is that because people generate these various particles from their favorite extensions to the standard model of particle physics, but this is in a sense it's a bit more phenomenological. So we say, okay, well, if dark matter has this property, how would it behave? What would it do? And you can kind of reverse engineer to say, well, if it's got this distribution, etc. Then the particle making it up should have this particular mass range and so on. So you can actually build a map from the fluid model to the particle physics model. We're basically just doing this the other way because we're in a sense we're particle agnostic.
Sorry, we've got a question online here from Prof. Aswandini Moronga. Have you actually replotted the rotating curves with your bulk viscous model yet?
No, that's a good point. No, we haven't. Yeah, I'm not sure what that would give us. Certainly, that would be a good way to constrain the parameters of the model. But yeah, that's a really good question.
Further questions? You.
Yeah, so thanks, Anslyn. That was great. Yeah, it's sort of a similar question. Well, I think the answer to that question is that you have to do a simulation because it's highly nonlinear. So you'd have to include your viscosity in your model. But the other question, which is sort of a more general question, is have you plotted a power spectrum that you would predict in this type of a model? That's sort of a well-measured quantity, right?
If you want to plot the power spectrum, you need to solve the density perturbation in the full relativity form, because P of K is just P dot delta. That delta need to be computed in the full relativity form.
Yeah. However, I think, sorry, you're arguing your own model.
It's a pedagogical technique. Please continue.
Is that essentially, you know, if the effects are relatively local, then you can use a Newtonian approximation, right? That's, yeah. I think it's not bad to try that, but maybe we can discuss later.
Maybe we can discuss it later. Okay, if there are no other urgent questions, we can refer all the discussion and the sparring matches about what to do to outside. Yeah. So, Anslyn, thank you very much for the very interesting.